talk is base change along Frobenius endomorphism and the Gorenstein property. So this talk is really about the structure of and properties of the category complexes of finite injected dimension over commutative continuing rings. Of course, complexes of finite injected dimension tell us a lot about the ring itself, and there's a lot of well-known results about this. For example, a local ring, RMK, is regular if and only if K has finite injective dimension. We also know that a local ring emits a finitely generated module of finite injective dimension has to be called Macaulay. And this is in one of the properties or the results that I'm going to use quite a bit here. This is due to Bass and to Faxby, actually, I believe. Commutative engineering admits a finitely generated module of finite injected dimension and finite projective dimension if and only if R is Gorenstein. And of course, if R is Gorenstein, the categories of finite injective dimension and finite projective dimension coincide. All right, so I want to set up some settings and notation here. So RMK will always be a local ring, which is always assumed to have unitary and terion. So my talk is not really about the Frobenius endomorphism, and that was a clever ruse on my part to get people interested in this. But in fact, everything I'm saying is holds true for a more general class of endomorphisms, and those are called contracting endomorphisms, and those were defined by Arvamov, Einger, and Miller, I believe. So endomorphism phi is said to be contracting if phi to the power of I takes m into m squared for some I larger than 0. And of course, the Frobenius, when I is equals to 1, you already have phi takes m into m squared. And when I have a contracting endomorphism, I set R phi to be R, but with the right module structure induced by phi. And by IR, I will denote the subcategory of complexes of finite injective dimension. I of GR will be the subcategory of IR, consisting of complexes with finitely generated homology. And I of LR is subcategory of I of GR, consisting of complexes with finite length homology. So let me give you a few examples of contracting endomorphisms. So in characteristic P, in positive characteristic, the Frobenius endomorphism is obviously contracting.
Can I interrupt with a question?
Yes, sure.
When you say finite length homology, you mean each homology module is finite length?
So
like each degree?
So I mean each degree is finite length, but also the homology is bounded.
Okay, so whereas, and same question for finitely generated, I guess. Does that also include the assumption that the homology is bounded?
Yes.
Okay, thank you.
Sure. So let's say I have a ring kxy mod out by x cubed y cubed, and then I set phi takes x to y and y to y squared. So phi does not take m into m squared, but phi squared will take m into m squared. So this is an example of contracting endomorphism in every characteristics. And there are interesting examples coming from semi-group rings, but I'm not going to get into that. A lot of results that are known for the Frobenius have later been proved to be true for contracting endomorphisms in general. Arvamov, Einger, and Miller, for example, prove Kunz's theorem for contracting. And there's been a lot of results along the lines of the Frobenius results for contracting endomorphisms. So let me give some motivation why I got interested in this subject. There's a paper by Brittany Fallalow and Thomas Marley in 2018, and they have this theorem. So let phi be a contracting endomorphism on a Cohen-Macaulay local ring, and omega R the canonical module. Then the injective dimension of R phi tensor with omega R is finite if and only if R is Gorenstein. And then they asked this question: does this theorem hold if we replace omega R with a dualizing complex? And immediately answered no. And they give an example of a non-Cohen-Macaulay ring, which has a dualizing complex, and they show that when you take this tensor product, the injective dimension stays finite, but obviously the ring is not Cohen-Macaulay, so hence it's not Gorenstein. And just a quick reminder, a complex D is dualizing if the following hold. First of all, the D has finite injective dimension. HD, the homology is finitely generated.
And can you remind us again, what does it exactly mean for a complex to have finite injective dimension? I forget now what it exactly means.
So it means that it's quasi-isomorphic to a bounded complex of injective modules.
Oh, okay. Okay, that's okay. Makes sense. Okay.
So a dualizing complex has finite injective dimension, finitely generated homology, and the natural map R to R ham DD is a quasi-isomorphism. So then Fallalow Marley posed a question. So instead of looking at the tensor product, what if we look at the derived tensor product? So let's phi be a contracting endomorphism and D a dualizing complex. If the derived tensor product of R, phi, and D has finite injective dimension, is R necessarily Gorenstein? So this question got me into this subject, and not to keep the audience suspense, the answer is yes. In fact, what I'm going to prove is something a little bit stronger. So let me get to the main result of this talk, and then I will explain, give a little outline on how I'm going to prove it, dissect a little bit the outline, and then show what tricks I'm using to actually prove this.
That last theorem was not under the Cohen-Macaulay hypothesis.
So if you have a Cohen-Macaulay ring, then a dualizing complex is in fact a dualizing module, which is really a canonical module.
Got it. So it's a general. So this is an attempt to generalize to non-Cohen-Macaulay rings by replacing the canonical module with the dualizing.
So I'm not sure if it's an actual generalization. So that's an interesting question. So Fallalow Marley showed that replacing omega R with a dualizing complex cannot work, right? Well, so the thing. So the thing I'm not so sure about is that here I'm looking at the derived tensor product, and I'm not sure that if I can show that the derived tensor product is has finite injective dimension, doesn't necessarily mean that the actual tensor product has finite injective dimension, even for a canonical module. So I don't want to say I'm generalizing. I prefer to say I'm giving an analog.
Yeah. So that last part I didn't really extend, because what I'm thinking, if your result is true, then the ring is in particular Cohen-Macaulay. So the dualizing complex is actually a module. And is then the derived tensor product still different from if you take direct a tensor product, derived tensor product from two modules? Is that not just a regular tensor product? But I'm missing something.
No, the derived tensor product wouldn't be the same if neither of those modules have finite flat dimension, right? The way you define the derived tensor product is you replace one of the modules with a flat resolution.
Okay.
Right,
sorry, yeah, I'm not so well versed in this derived column knowledge. Okay, sorry, yeah, no, then it's not the same. Okay, gotcha.
Yeah, but I'm actually not. I actually don't know if it would imply if I know it's true for the derived tensor product.
Yeah, but not for the obvious reason that I was saying.
Yeah,
okay,
yeah. All right. So let me state the main theorem. So let phi from R to R to be a contracting endomorphism. So then the following are equivalent. One, R is Gorenstein. Two, there exists an R complex in IFGR, which in other words, a complex with finite injective dimension, finitely generated homology. And of course, I want non-trivial homology, such that the derived tensor product of R phi and X is finite. Equivalently, for every X in IFGR, we have the injective dimension of this derived tensor product is finite. So let me outline how this proof is going to go. The first two directions are easy. So 1 implies 3 is easy, and this is due to Foxby because Foxby showed that Gorenstein ring complexes of finite injective dimension are the perfect complexes. In other words, the complexes of finite projective dimension. And obviously, when you take a base change, the projective dimension does not go up. So the finite projective dimension stays the same, but then you're still in the Gorenstein ring. 3 implies 2 is easy. The only thing we need to show really is that every local ring has a complex in IFGR with non-zero homology. And if you take the complex KR, which is the Kazoo complex in the minimal generating set on the maximal ideal, and I tensor that with injective Hall of the residue field, it's not too hard to show that this is non-zero. It has non-zero homology, and then the EK is Artinian. On the other hand, M annihilates the KR. So this is a exercise in Brunson-Herzog to show that this actually has finite linked homology. So the new implication is 2 implies 1, that if I have a non-trivial complex of finite injective dimension and the derived tensor product with R phi is finite, has finite injective dimension, then R is Gorenstein. So let me outline how I'm going to prove 2 implies 1. So let's start with the complex X and IFGR with non-zero homology, and we'll assume that the derived tensor product of R phi with X has finite injective dimension. We have this series of implications. First I can reduce it to the case where I have something and I have Y, which is IFLR, so Y has finite linked homology, non-zero homology, and this injective dimension is finite. And this is very easy. You just tensor with the Kazoo complex, and that's one of the tricks to keep using. Keep tensoring the Kazoo complex, makes life easier. Then once I have A, that will imply that for every Y in IFLR, we have this, the injective dimension of this derived tensor product will be finite. And this is non-trivial and probably be the bulk of my talk, showing how we go from A to B. I forgot to mention one thing. When I'm looking at this injective dimension, this might be a little confusing. It certainly wasn't that obvious to me on first reading. When I'm looking at the injective dimension, I'm really looking at the injective dimension of this derived tensor product in the target ring, not in the source. Aronov, Eing, and Miller have already proven that this derived tensor product will have finite injective dimension over the source ring if and only if R is regular. So keep in mind this R is really viewing in the target. All right, so B will imply that.
Wait, now you
I
lost.
apologize, I missed. Yeah. Sorry, go ahead.
Because what is an R phi? R phi is the target, right?
Yeah, R phi is the target, but viewed as a module over the source.
Okay, you then tensor it, and now it becomes a module. And now you view this as a module over R phi.
Yeah, I'm viewing it as a complex over. Yeah.
Okay, so you would actually have to write injective dimension R phi here in the subscript.
So maybe then becomes more confusing because.
Yeah. Okay. Right. I see. No. Right. That's not a ring. That's not a ring R phi. Right.
Yeah.
Right. Yes.
So, but then what is this? What's the target? Like, I'm just lost on why I only see R. What's the other ring?
It's an endomorphism, right? You can view R two different ways. It's an endomorphism from R to R,
Sure.
and there's two different structures here going on this derived tensor product. There's this modules, this complex structure coming from the ring itself, and then this structure coming from R phi, which is over the source. Where if you multiply by any element, you have to take phi of that element. Does that answer your question?
I'm going to need to think about it for a minute just to see what it would mean to see something as a module over the target.
Think of the Frobenius.
Sure.
Right? You have a module or the Frobenius endomorphism. You have two different actions, right? You can view it
right
where you have to push everything to the Frobenius, or you take the Frobenius. Now you still have a module over this ring, and now you can just view whatever you get.
Right, but everything in sight is an R module.
Yes, but there is two separate structures you can look at.
I mean, everything in sight is a module over the. In my mind, up until this point, everything in sight was a module over the source.
Yes.
But now the left-hand side of the tensor product is also a module over the target.
Got it.
That's exactly what it means. So
that's the point.
That's the point.
Got it. Okay. Thank you, Hans. That was just what I needed to hear.
Okay. So once I know that for every y in IFLR we have this derived tensor product has finite injective dimension. Well, so now I'm looking at this complex R phi derived tensor product with y, and I know it has finite injective dimension. I know it has finite length. And now I can forget about that this complex comes from some y, and I just take phi again, right? And what?
Yeah.
So when I do that, I already know that whatever I get out of that is also going to have finite injective dimension, finite length homology over the new target ring. So in other words, I can keep pushing this for every I bigger than 0. I know that the injective dimension over the new source, the new target ring of R phi to the power of I derived tensor with y has finite injective dimension.
Tu non hai la tua accreditata.
Sorry, was that a question? All right. So C would imply that y actually had to have projected dimension to begin with, and here I'm taking obviously projected dimension over the source ring, and this also takes a little bit of work, but of course D implies that R is Gorenstein because this is already due to Foxby, because now I have something with finite projected dimension, finite injective dimension, and Foxby proved that such a ring has to be Gorenstein. So now I want to focus on how how I go from A to B. So I need to set up some notation and introduce some concepts. So the notion we need is the notion of a tick subcategory. So definition, a non-empty subcategory T of the derived category is tick if it's full, it's closed undertaking direct summand, and it satisfies the 2 out of 3 property. In other words, for every exact triangle, if two of the complexes are in T, so does the third. And some examples, which is very fortunate, that the IFGR, IFLR, and the perfect complexes, which I'm using in the stock, these are all tick subcategories. Now, given a complex in the derived category, I can define the tick subcategory generated by X. I will denote that as tick X. So this is the smallest tick subcategory that contains X, and it could be obtained as the intersection of all tick subcategories and the derived category that contains X. It's not too hard to see that when you take intersections of tick subcategories, what you get out is also a tick subcategory. So, for example, if you have an Artinian ring, then we always have the tick R of the ring itself. These are all the perfect complexes. So in other words, these are the complexes of finite injector dimension. When I have a local ring, and we have the tick subcategory generated by the residue field, these are complexes with bounded homology, bounded finite linked homology. In some sense, tick of a complex is all the complexes you can build by taking like finite extensions or direct sums and whatnot after finitely many steps.
Sorry, I forgot the previous slide. It said a bit of is it closed on the direct summand or only just direct sums?
The direct summand.
Ah, summand, right? Okay. Yes. Okay.
Yes. Let's see how we're doing that. There is a constructive way of doing tick X, but maybe I will skip it. Yeah, I think in the interest of time, I will skip that part. There is. It's good to know there is a constructive way of building this finitely, but we're not going to need that in this talk. So tick subcategories behave nicely on their exact functors, and by that I mean if I have an exact functor from the derived category of R to the derived category of S, then the image of a tick subcategory generated by X is contained in the tick subcategory in S that is generated by the image of X. Another thing it's good to know is that for every X in the derived category and any perfect complex P, the complexes P derived tensor X and R ham PX, these are all contained in the tick subcategory generated by X. And people have used this to show many things. Dwyer, Greenless, and Miller or Inger. I don't remember who it was. There's a lot of results coming from these kinds of along these lines. People have used these to get a lot of results. So there is a connection between tick subcategories and support. So the support of an R complex is defined to be all the prime ideals that support the homology. And it's not too hard to see that when Y is contained in in tick subcategory generated by X, then the support of Y is contained in the support of X. And it's not too hard to see. For example, if you take some prime ideal that is not in support of X, you can apply this exact localization function, and you will see that YP has to be contained in a tick subcategory generated by 0. So that's one way of proving it. You can also look at if you know how to do the constructive way of building tick X, there's another way of seeing that. So, but the converse does not hold in general. So you can have complexes which you can have a complex Y, which the support of Y is contained in X, but the tick subcategory Y will not be in the tick subcategory generated by X. And the easy example is if you take any non-regular ring, support of any complex is going to be contained in the support of R, but the tick subcategory generated by R, as we have seen earlier, these are the perfect complexes. And obviously, if not every complex is perfect, if the ring is not regular, not every complex is perfect. So the converse doesn't hold. However, it does hold for perfect complexes, and this is due to Hopkins and Niemann. So Hopkins and Niemann proved that if you have a commutative Noetherian ring and you have given two perfect R complexes and an M, if the support of N is contained in support of M, then N has to be contained in the tick subcategory generated by M. And
Pinch?
Yes.
Can you briefly mention what's the perfect R complex, or can you give an example of
that? Perfect complexes is complexes of finite projective dimension.
Oh, okay.
Okay. Yes, that's a good point. I'm just used to call them perfect complexes. And the proof of this is left as an exercise to the reader. It's highly non-trivial. You got to go to tensor triangulate categories.
Oh, this was a joke. Okay, I was always sort of freaking out.
Yeah, no.
It's amazing that this would be true. Even I'm really puzzled that this such result can hold. But okay. Yeah. Mm-hmm.
Yeah. So I was attended once a talk by Shri. I don't remember who he quoted, but somebody said that every math talk needs to have a joke and a theorem and a proof, and the audience needs to be able to tell the difference. So this was my attempt as a joke. So Hopkins and Niemann is very useful in many situations, and very often simplifies proofs. And
do you know when this was proven? This result?
Ooh, I don't remember on top of my head. I do know that Hopkins' original proof had some problem, and which was fixed by Niemann. So it was a few year difference there, but I don't actually remember when it was proven.
Approximately, are we talking?
I believe it was in the late 70s, maybe, or 80s.
It's that old already, because I know neither one. So I don't know who these are, these Hopkins and Niemann. So, but that might be my ignorance. Yeah, okay.
Yeah, but I might be wrong about this.
Yeah, okay.
So Hopkins and Niemann is very useful in many situations. One of my favorite examples, and this is something that still baffles me a little bit, and I've tried to work on this. So if I have a regular local ring, then K is in the tick subcategory generated by X for every X in which has bounded finite linked homology. If you view this in the derived category, because obviously in a regular local ring, K is a perfect complex, and you can apply Hopkins and Niemann. However, if you look in the module category, this is not known in characteristic 0. It is known in characteristic P and due to Takashi, but it's not known whether this falls in characteristic 0, which is very strange to me. But in the drive category, you can apply Happenstein, so it's much easier. So I'm going to use a analog or a partial analog of Happenstein to prove the implication A implies B. If there is any questions, I see is the people chatting, but I can't actually see the chat, so.
Faye just found the papers. Hopkins was 85 and Neiman was 91. That's the check.
Okay. It's just all right.
Hopefully those are right references.
Probably. So proposition is that for every X in IFLR with non-zero homology, one has that the tick subcategory generated by X is equals to the entire category of IFLR. And in the outline of the proof, well, clearly we already seen that IFLR is a tick subcategory and X is an IFLR, so clearly tick X is contained in IFLR. So we only need to show that for every Y in IFLR, we have Y as in the tick subcategory generated by X. So the way we prove this, take the matless dual. Now this is a perfect complex that is supported at M. By Happenstein, YV is contained in the tick subcategory generated by XV. Right? But then I apply the matless dual again, so I get that YW is contained in tick subcategory generated by XW, because this is a exact functor. And of course, when you take the double matless dual of any complex, you get back the completion. However, we're starting something that has finite length. In particular, is supported to the maximal ideal. So this is already, Y was already complete. So Y is quasi-isomorphic to its completion. So this proves the proposition. So I'm going to use this proposition to prove A implies B. So corollary, if there exists any X in IFLR with non-zero homology such that the finite injective dimension of this derived tensor product with phi, with our phi is finite, then for every Y in IFLR we have the derived tensor product is finite, has finite injective dimension. And the proof is pretty easy, since Y is in tick X, we have that this derived tensor product of R phi with Y is in the tick subcategory generated by the image of X under this derived tensor product. But by assumption, this has finite length homology and it's non-zero. So this tick subcategory is equals to by the proposition to IFLR. So that shows that the implication A implies B. All right. So
why did you have to go to the powers of phi? I lost the reason for.
Oh yeah. Oh, so the reason I went to the powers of phi here is because I made a typo.
Okay.
Yeah, I copied the wrong code.
Okay.
But yeah, thank you for pointing that out.
Can you go back to this? Oh yeah, that one. I was about to ask to go.
Yes. So now we have A implies B. B implies C. We have already talked about. This is just induction. So now I want to show how I go from C implies D. So if I know that for every y in IFLR, and for every I bigger than 0, we have the finite injective dimension of R phi to the I derived tensor with y has finite injective dimension, I want to show that this will actually show that y has finite projective dimension. And to do this, we
which
need
y? Every y. I mean, there's a y in the first sentence, and what is the y in the second? Which y?
I'm looking everyone, except, well, yeah. I want to have obviously a y which has non-trivial homology, because it's going to be trivially true for y is trivial. There's nothing to show. Okay, so for that we need the notion of Lowy length. So if RMK is a local ring, an extra complex of R modules, then the Lowy length of X is defined to be the infimum of I, such that m to the power of I times X is the zero complex. And the homotopical lower length of X is defined to be, so the lower length is denoted LLX, and the homotopical lower length is, I'm showing this is in the derived category. So this is the infimum of all the lower lengths of V, where V is quasi-isomorphic to X. And Arvamov, Iyengar, and Miller have proven that this Lowy length satisfies some finiteness condition or finiteness property. So on a local, so let RMK be a local ring, and Ka the Gazul complex on a minimal generating set of M. Now for every complex X, we have the Lowy length, the homotopical Lowy length of Kr tensor with X is bounded by the Lowy length of Kr, and that's always finite. And then there is actually an upper bound. I don't remember on top of my head what it is, but it's sufficient for us to know that there is this Lowy length of the Gazul complex is finite.
But in the derived category, not of the complex itself. It is another complex that is isomorphic with it, or it's the actual complex.
I'm not sure if it's the actual complex.
Okay.
I don't remember.
Okay.
But the homotopical lower length is definitely finite. That's all we need, because we are working in the derived category. All right. So let's make a proposition. So let phi from R to S be a local homomorphism such that phi of M, phi takes M into NC, where C is the homotopical Lowy length of KS, the Gazul complex in S. Then for any X with finitely generated homology and bounded below finitely generated homology, we have this Tor R S and X is 0 for large I, if and only if X has finite projective dimension. So let me just point out what is happening here. When I go to this, if I'm assuming this phi takes M into NC, which C is the lower length of KS, then multiplication on KS by any element in R is really multiplying with something in NC, but that's, since C is in the homotopical lower length, if you're multiplying anything by anything in M, you multiplying, you get 0, right? So this R action on this particular homomorphism factors through the residue field of R, and that's why I'm looking at these high enough endomorphisms. So how is this proof going to go? So the if part is clear. if you start with something that has finite projective dimension, taking the base change gives you something with finite projective dimension. Of course, then the torr is going to be 0 for a large enough I. For the converse, we know that if I look at the supremum where h of the derived tensor product is non-zero, if that's finite, then tensoring by Ks, which is just a complex of finite projective dimension, is also going to have bounded homology, right? But the complex Ks is quasi-isomorphic to its homology in dr, and because effect is through this the residue field. So really, Ks or H of Ks, the homology has a K vector space structure as an R complex. So now I can use the Knut formulas and to show that the homology of Ks tensor with X is quasi-isomorphic to the homology of Ks tensor over K with H of K derived tensor with X. But since I assume that the left-hand side is bounded, then the right-hand side is bounded. In particular, this part is bounded, right? But this is really measuring the projective dimension of X itself. So if I know that this homology is bounded, the projective dimension of X is finite. And so the reason why we want this proposition is if I start with a contracting endomorphism phi from R to itself, then if I take I large enough, eventually phi to the I is going to take M into MC, where C is the Lowy length of the Kazoo complex on R. So if I know the complex R phi I tensor X has bounded homology for all I bigger than 0, that can only happen if and only if X has finite projective dimension, which is giving me, so this is giving me the implication C implies D. So maybe let me point out there's two parts here. So for A implies B, I really needed to know that Y has finite projective dimension. I didn't use any facts about R being phi being a contracting endomorphism. I'm just using that we have this endomorphism, and I just used the analog of Hopkins and Niemann to show that if I start with something finite projective dimension that stays finite projective dimension after taking one phi is going to stay finite projective dimension no matter how many phis I'm taking. And then for C implies D, I'm really using the fact that phi is a contracting endomorphism, and I'm just using the fact that Y has bounded and finitely generated homology. So there's like two different steps here. So what I'm trying to say here is.
But what is then the last step of the proof? Is that also from D to E?
On D to E, this is just Foxby. Now you have a complex of finite injective dimension, finite projective dimension.
Oh, okay. Y is also finite injective dimension. I forgot
yeah.
what Y was. Yeah. So I didn't. Why did you need to go from sum to all? Where is the sum to all used later on? I know you did it. Yeah.
So I need to know that I can push phi large enough that that phi I takes M into the M to the C, where C is the Lowy length.
Oh, okay. But for instance, for the Frobenius, you wouldn't. Yeah. Okay. You still would not know. Oh, yeah. Okay. I see what you mean. Okay.
Yeah. So
for Frobenius, you might need to know it for. Yeah. Okay.
So the point here is, if you start with any complex of non-finite injective dimension or non-finite projective dimension and you have this contracting endomorphism, eventually, if you take phi large enough, phi I large enough, you're going to end up with a complex that has unbounded homology, right? But it could happen that you take the first step and you have something that has bounded homology, but then you keep pushing it, and eventually you're going to end up with something with unbounded homology, since you're starting something that doesn't have finite projective dimension. What this theorem is showing, that if you have the additional assumption that your complex has finite injective dimension, then you just have two possibilities. Either the complex stays with finite injective dimension after the first step, and then it stays after the second and for every step, or it has to blow up right away. There is no intermediate steps. And this is where you really need a finite injective dimension. So let me give an example of a complex that doesn't have finite projective dimension, also doesn't have finite injective dimension, where you take the first step under a contracting endomorphism, it still stays bounded, but obviously eventually cannot stay bounded. So let me give you the same example I had earlier. So R is kxy mod by x cubed y cubed, and x is y, and y gets mapped to y squared. So I'm looking at this complex R to R. So really, this is so what I have here. This is just the resolution of R mod x, right? So if I'm taking this complex, if I apply R phi to this, I'm just replacing every x with y. So it's very easy to see that R phi tensor with x is quasi-isomorphic to R mod y. So clearly this has finite homology. But if you take this again, then if you take phi squared, then the x squareds get mapped to 0. And this x gets mapped to y squared. And clearly this will have unbounded homology. So if I don't have finite injective dimension, I could end up in a situation where I have these intermediate steps. I start out, first I'm a K, and eventually blows up. Any questions?
So even the result, you proved it for contracting, but even for Frobenius, you're saying this is new, right?
Yes.
Yeah. Okay. It was just convenient to have it. It doesn't make a difference to prove it for
Yeah, I'm not using any of the Frobenius, anything that's special Frobenius.
Right.
The only thing I'm really using is that eventually phi maps m to m squared.
Mm-hmm. Right. Any other questions, guys?
Would you go back to the slide that has the global structure of the argument? I don't really have a question, but I just want to grok that slide again. The one that has ABCD.
This one, the one, yeah, that's one I think he means.
Yeah, that's the one.
So the x you started with, then the y that was just the derived tensor with the causal complex, right?
Yes.
And then the y that you get in D is a twist by a certain twist after a couple of by phi. That's what it is.
Which one?
The last one in land D. It's not the original y anymore.
It's the original y. It's the original y, right? So here I'm looking. So I'm starting out with some y in IFLR, right?
Right. Mm-hmm.
I can show that if I keep pushing this y with the twist on along phi to the I always stay finite injective dimension, but that forces me to have that Y had to have finite projected dimension to begin with.
Okay. Oh, okay. Yeah, right. That's okay. Yes. Okay. So, right. You need, okay. Here we needed this. That's for all I there. Okay. For I and off. Okay. From C to D. Okay.
Which step is the step that exploits the fact that the map is contracting?
C to D. So C to D will be true. More general, you can say that for any complex that has bounded homology, bounded finite degenerate homology, if the twist along phi I for I large enough has bounded homology, then your complex has finite projected dimension. If he's contracting.
And that's Foxby?
No, this is using this
The lower
the lower length. I'm pretty sure that this argument this argument has been known for a while. I don't know if anybody has written down explicitly in the literature, but this is, people have used this kind of argument before.
And then the fact that phi is an endomorphism, that's used.
That's used to for me to push this.
Yeah.
Because I need to be able to push phi into M into MC.
Yeah.